Welcome to another episode of Power Insights, Power Magazine's video interview series. I'm Aaron Larson, Executive Editor of Power, and on this episode, I'm joined by Dr. Richard Buttery. Richard is the Director of Experimental Science for the DIIID National Fusion Facility, which is operated by General Atomics in San Diego, California. Fusion has long been seen as the holy grail for the energy industry. Yet we're probably still many years away from achieving usable energy from a fusion reaction. Still, a lot of work is being done, not only in San Diego, but around the world, and Dr. Buttery gives his insight on some of the progress being made. Before we begin, I'd like to thank our sponsor, the 2021 Connected Plant Conference. For more information about the event, please visit www.connectedplantconference.com. Richard, I'm so excited to have you here. Thanks for joining me. Now, as I understand it, the DIIID facility is a U.S. Department of Energy national user facility, which is operated by General Atomics in San Diego on behalf of the DOE Office of Science. There's a lot to digest there. Can you tell a little bit about the DIIID facility and how it has evolved over time?
DIIID is a tokamak, which means it's a device that holds very hot gas together. The gas is shaped like a donut, and we use magnetic fields to hold that plasma together. It's called a plasma. It's called a plasma because it's very hot, and it gets so hot it's ionized. When you get gases to very high temperatures, if you have the right ingredients, they will fuse, just like in the sun, and release energy. And so on Earth, we do this with a tokamak using the magnetic fields to basically hold the plasma in a shape. It's a donut shaped, so you can see the device behind me. It's just an image behind me. I'm not actually in the machine right now. That device holds this giant donut of plasma, and it gets incredibly hot in the center of the plasma. And we get fusion going on right in the middle. So just to give you some ideas, this is about 8 or 9 feet across. The plasmas are about 6 feet tall. So it's a really big donut of super hot plasma. And to give you one stat, in DIIID, we want to make fusion more efficiently than in the sun because we have to pay for all of our magnetic fields. So we operate at 10 times the temperature of the core of the sun in the middle of our plasmas. And then we have to get that all down to very low temperatures right at the edge of the plasma. And that's where our magnetic fields help us because they guide all the hot particles to stay in the middle, and that isolates the heat in the middle and keeps it trapped there where we can get it super hot for doing lots of fusion. So that's the idea of DIIID, and it's built on a succession of facilities as we've pioneered at General Atomics over the years. Initial machines with interesting shapes, a doublet shape we started with. We like the donut now, so D really is standing for donut now, but it used to mean doublet. And we got bigger, 1, 2, 3, and then we went to this D-shaped vessel that you can see behind me here.
I think it's incredibly fascinating, and I think it's interesting, and probably a lot of people don't realize that you're doing this. I mean, this is actual fusion taking place today in your lab. What does it take? You know, you mentioned very high temperatures. What temperatures are you getting up to, and how do you get to that point?
So we operate at something like 100 million degrees centigrade. To set that in context, you know, something you would think of as very hot might be thousands of degrees centigrade, and that would be super hot. So our plasmas are much, much hotter than that. The trick is, of course, they're much lower density. So actually their pressure is similar to atmospheric pressure, but there's very small amounts of plasma in there, but it's super hot, and that's enough to get going. I mean, to get there on DIIID, we use particle beam systems to heat up the plasma. So we just shine neutral particles into our plasma, or we use microwaves, a bit like your microwave at home, and that heats up the plasma and drives current in it and allows us to control it in various ways.
I'd like to talk about some of the other things that are taking place around the world, because obviously there's the ITER project and there's some other projects that are doing similar work. Do you build on lessons from each of these projects and kind of incorporate them? Or do you work together with scientists in other parts of the world to develop new options and technologies?
Yeah, it's a very collaborative program. I mean, D3D, we host a wide range of institutions here, from national labs, from top universities like Columbia and MIT, but also we collaborate with international colleagues. So there are other labs around the world that do fusion, that have different types of devices. We like to think our device occupies a particular niche in that it's extremely flexible, and it has a huge amount of measurement systems. So we can really try things out and see what's going on, figure out how to make it better, and figure out how it works so that we can make simulations and project future reactors. So ours is sort of, we just seem to be occupying a nice sweet spot in where we can figure out stuff. There are other facilities around the world. In Europe, they have JET, which is a slightly larger facility, so we can use that to scale up a little bit towards a next device. And they're building a power plant scale fusion device in the south of France, as you said, called ITER, which is Latin for the way. And that's actually going to be big enough that the heating from the fusion will keep the plasma hot. So it will just keep itself going mostly with just a very small amount of heating power. So that's going to prove one important part of the problem. The other thing we're looking at is how do we then sustain that plasma? How do we go for steady state? What we'd like is a power plant that you just turn on and it just runs continuously. So at present plasmas, we ramp up a current in them. We can use that current to shape the plasma and control it in various ways. But at some point you're inducing that current, you run out of induction capacity. So what we would like to do is go steady state, where we drive that current with particle beams or with effects that just generate the current naturally within the plasma. That's called bootstrap. So we're working on, as well as supporting this ITER device, we're working on how do we stretch out that plasma and just run it indefinitely, get it completely stationary, and you just switch it on and it's good. And so this is something D3D is really wanting to look forward to for the future. You know, we're trying out various techniques to do that at the moment. We've had a big upgrade with our beam heating system to deposit the beams differently in the plasma. And we've implemented one, and we're commissioning 2 more current drive systems that will explore how to sustain the plasma. So there's a lot going on and a lot to figure out, and it's kind of exciting.
So I guess, as you said, there's a lot to figure out. Do you typically see like leaps forward where you just make this incredible discovery that, oh, if we do it this way, we can manage something that we have been struggling with for a long time? Or do you just kind of keep taking small steps along the way and just seem to keep making a little bit of progress every day?
Well, it's a bit of both. I mean, you really want to make those big steps where you figure out how to do something, where you know, one day you couldn't control the heat burst coming out, and the next day, bam, you have a technique and it controls those heat bursts, and you've got lovely smooth power coming out that you can handle, right? So we've done things like that. So we always strive to try and find new things. So we try and do new things with our plasma. We're also implementing new systems to make our plasma try out new things. So I talked about, we've got these new current drive systems. We've changed, for example, in the upper region up here, you can see the power all gets handled by this structure above my head here. We can change the shape of that and find a way that will handle the power much more efficiently. So there's actually a lot of techniques where you can really have those these light bulb moments where you go, ah, this thing works. And sometimes we find it experimentally. And then other times our theorists, we work closely with theorists, they'll predict something and say, go and look there. And we go and look and we do find something, which is really satisfying. So that's really what we strive to do. But then the other thing you find is that when you have a solution, you want to know, is that going to work in a reactor? So, I need to understand it, because I need to understand how it's going to work at higher fields and energies and so on. So there's actually a lot of work just trying to really understand very precisely the physics of what's going on. So you might probe things with particle beams or pulses of heat, or try and switch an effect on and off in different ways to really understand it. And that's where the really deep science comes in. And so that is, in a sense, is more incremental. So, we control these heat burst instabilities. We did that in 2005. But it really took us 10 years to figure out all of the physics of that. And some parts we're still looking at now. And now we begin to understand how and we can apply it in the reactor, so you can design the reactor with more confidence. So it's both. The thing I like about this is it connects what is very rich physics. I'm a theoretical physicist by training. That's my PhD. But to a practicality of, if I understand this, if I can then figure out how to make something better, I have something very practical I can engineer and build and make it work.
So when you think about this actually down the road, and we're building power plants where we're actually generating electricity and making power that's usable on the grid and in places, what does it take to get from this point to that point, and how do you extract that energy? Is it a typical steam plant, what we're used to seeing at a regular nuclear plant or a coal plant, or is it something completely different and new that will be just kind of change the world?
Yeah, right. So the power plant, the part that makes the electricity, that's like known technology. So it's a steam plant, right? But the question is, how do you provide the heat into that? So you have you have your fusion plant running very hot. It extracts we call it high grade heat. That then converts to secondary coolant systems, which are the steam generators that run the power plant. So we're focused at DIIID on the plasma science of that. How do I make my plasma super hot and confine it and keep it going? And so that's one part, because the United States is now embracing a mission to build a very compact pilot plant. They want to build the first one, make it as quickly as possible, and that also means make it efficient and cheap and not too big to build. And so to do that, we actually have to make the plasma very high performing. Now we think we can do that. We do that on DIIID, but we want to understand better configurations that do that better and be able to project out how to do that in a reactor. So that's sort of one of the things we're trying to do. So there's a lot of plasma science, but then the other side is the technology. So I talked about current drive systems. How do those work? How do we make those work inside the pilot plant? Do we need antennas that launch the waves? How do we make those antennas compatible with the plasma environment? You've got a fair amount of heat flying around the place. So you've got to design that. You've got to have materials that can sustain the heat load coming off the plasma. We use our magnetic fields to structure it and mitigate as much as possible. But in the end, you've got a tile facing the plasma and it has to deal with something. So there's a lot of technology we need to understand. A fusion reactor will make a lot of neutrons. You can trap those in the breeding blanket and make your fusion fuel from those. So we have to understand how that works. But those neutrons can also damage the material. So we want a new generation of better structured materials that can work. And so we're looking at things like that. On DIIID, we're looking at things like silicon carbide, which sounds like a very promising material for handling neutron fluxes without its lattice being damaged. But many of these are technology programs that go off at places like Oak Ridge National Laboratory, where they're looking more fundamentally at the underlying technologies. So it's a combination of those two things coming together that will allow us to work out a design of a pilot plant that can prove all of the principles together.
And when you think about the size of these plants, you've mentioned what that tokamak size is, 8 feet tall or 6 feet in diameter. So what kind of power output would a facility like that produce, do you think, if it were to be a power plant? Are we talking thousands of megawatts, or are we talking less? Or
Well, there's a tension. We think the first one should be smaller because you want to prove the principles and work out how you will optimize the technologies. So we're looking at devices maybe 200, 300, 400 megawatts of electricity would be the pilot plant, the first one you do. And actually, that's not too far from where American utilities want to be at the moment. They like units of 0.5 gigawatt. That's sort of, you know, a larger amount is more difficult for them to manage in terms of loads on the grid. So actually it's not bad, but in principle, if you could do larger amounts of power, you may be able to make a cheaper device in terms of its final cost of electricity. So there's a tension between the first ones, we would like to keep the capital costs down and work out how to make it more efficiently. But then the later ones, maybe you can risk the investment a bit more, spend a bit more capital, but end up with a lower cost of electricity. So there's a path that we have to take through this.
And I guess my last question would be, how does it work as far as the fuel? Are you constantly putting more, because you're using hydrogen, right, to basically fuel the process. So are you constantly adding more hydrogen, and what happens to it when it goes through the process? Is there helium then being taken off and removed from this?
Yes, that's exactly right. So we're feeding in types of hydrogen. We have deuterium, which we can extract from seawater, and we have tritium, which we can breed in the walls of our device. The neutrons will hit a wall of lithium, and the lithium emits tritium when it gets neutrons. And so we're feeding that into the device. At the moment we use gas puffs. Possibly in a reactor we would use little pellets and fire them right into the center, and then that is all coming out. And here, some of this is the plasma physics as to how that comes out, and then that gets recycled. I mean, the JET facility has operated with tritium. TFTR was actually the first in the United States to operate with tritium. And so they had a big tritium handling plant where they could extract the gases coming out of the machine, extract the tritium in one direction, you know, helium goes another direction. And so you have to manage all of that. But that's actually not too difficult. Breeding the tritium is more challenging. That's something we really need to work on.
Okay. Well, is there anything else that you can think of that we haven't talked about that would be interesting and people would find fascinating?
Well, I think I would say that the other thing I've been involved in is I like the interconnectivity between the fusion goal and the basic science. I mean, on D3D, we've partnered with people doing solar physics and astrophysics to look at the fundamental processes of how energies move about, how magnetic fields reconnect with each other, how particles are given energy by waves and vice versa. It's terrifically interesting, and we've found a really strong connection with those other fields where they're going after the same understanding we are, but for quite different purposes. And so that's one of the things I find exciting about the United States. I think that the science is really good here. But also what's exciting is that we're now reorienting our fusion program towards a pilot plant goal and really moving forward on trying to come up with a practical fusion power plant that we could build soon. And that's really good news. If the United States can organize itself around that mission, I think it would be very interesting.
All right. Well, thank you so much for your time. I think this has been incredibly interesting, and I appreciate you explaining fusion and how the tokamak works and all the research and science that's going into it.
Okay, yeah, no problem. Anytime. Thank you.